Okay, so good afternoon, everyone. This is lecture 10. We are nearly reaching the midpoint for this course. The progress is good. We are covering almost at the rate of one chapter per week, which is what I intended. Okay. All right, so announcement. Don't forget the assignment 4, which is right after it's the next time we meet. Okay, so we will meet on 22nd of February. But before we meet next time, you have exercise classes next Thursday. Again, I would like to encourage you to go for the same reason that we put in time to prepare. And in particular, this is something the TA will spend the Lunar New Year vacation to prepare. So please, if you don't show up, the TAs might be very disappointed. Okay, so please do me a favor and attend these exercise classes. And assignment 5 will be uploaded sometimes around these days. Okay, so there's an assignment 5. The deadline will be, you just add another week here. So assignment 5, deadline will be around, so that is 29 February. Okay, and will be uploaded. Around the end of next week. Okay, so first, I want to show this slide. If you have seen my note, you should have realized this. I make 2 mistakes here, which somehow managed to percolate for many years, and it's the same mistake last year and the year before, and nobody picked up. Okay, so I take the responsibility, but at the same time, it's also funny because I ask students to try. You see, every time when you see this, I say the meaning is please try. So this showed me that last year nobody tried. Okay, so this is it's actually a very stupid mistake. I want a constant volume, but I take derivative, so that is nonsense. Okay, and unfortunately, it means the note is also wrong. That's why I say this is the same mistake that managed to stay for two rounds of this course. This is the 3rd time I teach this, so I thank Harry to point this out. Is it you? I'm sure it's you. Right? If it's not you, please say that. I will give credit to someone else. No, okay, sorry, someone else. I will now. The name is given in the updated version of the note. Okay, so when you when I will update all the notes today, and please replace everything with the latest version today. Okay, and if you spot any other mistake, please always let me know, and I will keep replacing. When you see draft, that is really draft. And if nothing needs to be replaced, I would just rename it. Okay, so who? Let me see. I think it's Wykin then. Sorry, is it you, Wong Wykin? I don't want to switch on my email, but if it's not you, okay, good. Thank you very much. Thank you for pointing this out. Okay, so recap. 1, this is the first table. So last lecture, we introduced really all this. Okay, so you have a lot to memorize, but what do you need to memorize? So let's have a look. This is something you need to memorize. This one. Okay, no excuse. So this is a big table for PDV system. So this is thermodynamic potential for a PV system. Okay, and the other thing you have to, I think, but with a little bit of help of the reasoning last week. So if you memorize this, and this, you will be fine. You'll be able to get this table without trouble. Okay, and I told you how to do this. The way to do this is to think about what kind of natural variable you want. What kind of natural variable you want. And then you just add or subtract an appropriate term. Okay, you can already do it. And if you get it wrong, you will know. Okay, if you correctly memorize the first law and the second law combined, and you know the natural variables, if you make a mistake, you will know. Okay, so this is not a problem. And I also presented to you, which is something aside, something additional, and it's not in the notes, is the fact that you can view this as the transformation. Then this can be, the enthalpy, the Helmholtz function, the Gibbs function can be obtained by appropriate Lejeune transformation, which is really talking about the geometry of a curve. Mathematically, this is the root of this transformation. How do you describe a curve? You can describe by giving a set of points, right? That will trace out the curve. Or you can equally provide the information of the local slope. That's the tangent for each point. So I gave you the derivation and I show you how to obtain different thermodynamic potentials that way. Okay, so this is the first derivative. The first derivative, when you write this function of state as some natural variables. Okay, so this is the derivatives. Okay, so this is one of the two tables. The first derivative gives you this, and the second derivative gives you the Maxwell relation. And these are the Maxwell relations based on different thermodynamic potentials. Okay, so this is again very useful. I hope at the end of today's lecture, you see some really quick calculations. The course is designed this way. I could have given you this right from the beginning, but this is not what I want. I want you to really take the longer path before. All right, that is your assignment 1 and 2. I hope you didn't cheat by using Maxwell relation. Once you know Maxwell relation, a lot of calculations can be done very quickly because you have various ways to change the partial derivatives. Look at this. This is completely different, right? So you have S here, and now S enters into the denominator. Okay, and I'm going to show you some examples. Okay, before we go there, I want to discuss one piece of physics, which is called the availability. This is something more general, and the ultimate aim is to show you how to use the concept of availability to decide which thermodynamic potentials to minimize. Okay, so we are going to go through this argument, and in fact, the end result, you could have just jumped to the end result and then say, this is obvious, and this is why we define the thermodynamic potential this way. Okay, and you hopefully you get this feeling later. Okay, well, I'm going to look at this scenario. So I will have a system, and this is my universe. Okay, so I'm going to close it outside. So this thick wall is outside the thick wall. I have no knowledge, so I'm going to look at this set as my universe. Okay, I have a system and surrounding. The surrounding, I'm going to take it to be big enough. So surrounding. Okay, let me put it very generally. So I have this system. This system is in contact with the surrounding, which is surrounding held at constant T0, P0. Okay, what is a good example of this? What is a good example of this surrounding? Really, this is your room. Okay, so if you have an experiment, let's say again my favorite example, in the chemistry lab, I have a beaker open to the room, and this will be something which I can describe this way. So I will have I'd say beaker, but what I really want to say is just imagine the beaker is just some boundary of the system. Okay, and then what I really want, the thermodynamic system will be that whatever liquid you put in the beaker. Okay, and in this case, what I want is to demand constant pressure and constant temperature, which is a very good approximation, right? The pressure will be 1 atmospheric pressure, and temperature will be room temperature. But I would like to give the possibility of changing the volume. Okay, that is to say, if my liquid somehow evaporates, I'm going to just look at the my thermodynamic system, this liquid, to be shrinking in volume. Okay, and my surrounding will be expanding in volume. Okay, so I allowed, now this discussion means I allowed volume change. Volume change. Okay, volume change is fine. What does it mean? I will allow work. Work is permitted. Work is permitted. I'm allowed to perform work on the system. And the other thing I would like to allow is I'm not going to say too much about the boundary. I'm going to also allow heat exchange. Okay, so the question is, if we want to discuss equilibrium, what is the appropriate thermodynamic potential function to minimize or to optimize? Thermodynamic potential to optimize. Okay, so if I want to discuss equilibrium, what is the appropriate thermal potential to optimize? Now here, this is set up in a way that is so general that you can discuss different constraints. So the quick answer is it depends. It depends on the constraints you impose. Constraints. It depends on the constraint imposed. So this is discussed very beautifully in Blundell and Atkins. So this is something you can read up. Okay. All right, let's begin. Okay, it depends on the constraint. So I would naturally need something general enough for me to later impose a constraint and tell you which thermodynamic potential function to use. Okay, so the scenario, let me set up the scenario. So I'm going to transfer internal energy, du, and the volume, right? Because I am allowed to do this. Right? Heat can go in. I'm going to use something more general. So I'm going to transfer the internal energy and volume. How much do I transfer? I'm going to transfer some infinitesimal amount of internal energy and a tiny amount, minute amount of volume. In thermodynamics, sign is important. So we need to build in this sign information. So I'm going to transfer from surrounding to the system. Okay, so that is to say, I'm going to now later I can have a minus sign to discuss the opposite, but I can then write down something like this. I'm going to transfer some internal energy du, so some internal energy du. Okay, so if I want to look at the change of the internal energy of my surrounding, which I will give a symbol naught. So this is a change of the internal energy after this transfer. And this has to acquire a minus sign. Okay, so this is my definition. Okay, so in other words, this is basically saying that if I gain some internal energy du, my surrounding will lose the same amount of internal energy. So that's where this minus sign is coming from. Okay, and I'm going to put this naught to label the surrounding P naught, T naught, just to be consistent. And this is also consistent with my notes and consistent with Blundell and Blundell. Okay, so now I'm going to write the first law for the surrounding. I'm going to see this surrounding as my thermodynamic system. I'm going to write the first law. Okay, so I have TdS minus PdV. P naught dV naught. Okay, but I don't want to introduce more symbol. I'm going to use the same thing again. So this is dV naught. Okay, but up here I already say the volume change is dV without the naught. Okay, so this is with respect to the system. So I'm going to just use the same symbol and put a minus sign. Okay, so this is first law. So this is first law and second law combined. I will just, from now, I will just say first law for surrounding. Okay, you have seen something similar. I use something less general when I discussed the Helmholtz function. I told you how to get this work done. The maximum work done you can have is the system's free energy, right? So this is a very similar discussion, but more general, a lot more general. Okay, let's, that's it actually. We just have to change the symbol. So we have ds naught. I want ds naught to be my subject. Wait a minute, let me see. So this is minus du. And then I want this term over there. So this is minus P naught dV. And then I have a T naught. Okay, let me tidy up the expression. So I have du plus P naught dV over T naught. Okay, so what is this? This is the entropy change for the surrounding. Okay, what do you do next? You do the same thing. You do the same thing as last time. you look at the entropy change of the universe here, you cannot say too much. But you can impose the second law like this. So the total entropy has to increase. Okay, that is to say, I will have ds plus ds naught has to be greater and equal to 0. Although this is, I have said this many times, but in the past, I have still seen students putting 0 here, right? Because somehow they see this du naught. If I move this du here, I will have du naught plus du is 0. Okay, and likewise for dv. And then sometimes students will do the same, ds plus ds naught is 0. I don't know why this is the case, but we really have to emphasize this. This is again the difficulty of about the second law. You can have conservation of energy, but this entropy is not something, a quantity which you conserve. Right? If you have an isolated system, thermally isolated, that is to say your universe, entropy can be created this way. So this is something you should keep in mind when you celebrate your Lunar New Year. And this is nothing much than the second law, nothing more than just the second law. So first law is here, second law is here. Okay. All right. So I plug in this one. I have ds naught. I can plug it back. Then I have du plus p naught dv. T naught is greater than 0. Okay, this is a good thing to have. Why? Because you see, we have everything written in terms of the system, except these two quantities that we know. If I know my surrounding, I will know. I will have full knowledge about P naught and T naught. Okay, so that is the key. If I change a different surrounding, I will have different P naught, T naught. So this analysis is applicable when you choose a particular surrounding. For example, my office here. If I go to your home, maybe this will be different. Maybe your T naught is higher, or you have a better heater than me. Okay, so this is the key. And everything else is written in terms of the system parameter. Okay, so rearrange this. I will have du plus p naught dv minus t naught ds is less than or equal to 0. Okay, you should convince yourself that this is correct. Okay, here we go. I'm going to define availability A. Symbol is A. And I'm going to define it this way. This is U plus P naught B minus T naught S. Okay, and with this definition, this equation will become dA has to be at most 0. Okay, you have seen something similar. You see ds total. Okay, this is here written here. ds of the universe has to be greater or equal to 0. And now you have the opposite. And this is based on the second law. Okay, so let me say a little bit more about this, and then we can start to play with this. Now, when this is developed for us to discuss equilibrium. Okay, so when a system, when a system approach the equilibrium, what do we know? We know S of the universe has to increase always, right? So this is always increases. But you see, this is kind of related. This kind of writing, you should by now be very comfortable with, and then you should also be able to interpret this correctly. Okay, so when a system in a particular surrounding approaches equilibrium, the surrounding plus the system, which is the universe, should have the entropy which is always increasing. And likewise, I can cast it in terms of the availability for my system in equilibrium with this particular surrounding. In this language, A must always decrease. So A always decreases. Okay, but it will keep doing so until you reach the equilibrium. So this is the process, this is the error. This is a process of going there. You are approaching equilibrium. Okay, but when equilibrium is reached, so at equilibrium, so what do we have? The S of universe has to be maximum. And then this has to be a minimum. Sorry, this writing is terrible. QNIV. Okay, so in other words, if I want to find the equilibrium, so to find, therefore, to find equilibrium, we need to minimize A. Okay, need to minimize A, and then what is the next thing to say? The next thing to say is subject to appropriate constraint. That is why we have all these constraint. That's why we have all these different thermodynamic potentials. Otherwise, we just come up with one. And that would be powerful enough. What is the next page? Eh? What did I do? This one has to be up. Okay, to give you a preview, this is what I want to do. Okay, when these are the constraints, when you have different constraints, what do you do? Okay, what do you want to minimize? What, in the end, we want to reach this page. Okay, so let's begin. This is a fun part. Okay, one. If we have constant entropy and constant volume, constant entropy and constant volume, what do we minimize? So constant entropy and constant volume, this is to say the ds, constant entropy and constant volume for the system. So I will have ds is 0, dv is 0. Okay, so I need to bring up this, where's the expression for A? It's very far. This is the expression we want. Okay, maybe I will do it differently. I will do it like this. Copy. Okay, and you look at this expression here and find the differential form. Actually, that is the one above. You will see, I will just write it out very quickly. So I have dA is du plus P naught dV, right? Because this is a constant. So when I do the differential, I don't care. And then this is ds. So I have ds is 0, dv is 0. So when I impose this constraint, this is 0, this is 0. I only have du. Okay, and when I approach minimum, I demand dA to be less than or equal to 0. So essentially, if I know my constraints, these are my constraints, I know this constraint translates to the minimization of the internal energy. Okay, so I will just write it for you. So need to minimize U. Okay, so this gives you the first entry on the table. Okay, so I'm going to flip the page. I want you to look at this again. Constant entropy, constant volume. I want to minimize internal energy. Okay, constant entropy, constant volume. I want to minimize the internal energy. That is the first entry done. Okay. All right. Let's do the next one. So the next one is constant entropy and constant pressure. Constant entropy and constant pressure. So let me copy this. I will need it later. So constant pressure. Constant pressure. And this constant pressure means my pressure is the same as the surrounding too. So this is the bigger example I want to emphasize. Okay, once I open this, what allows me to maintain this constant pressure? So this is the surrounding which give me this. Okay, and now I will just very quickly write the differential form. I will have dA, which is du, and this constant, I have constant pressure, P naught, and constant pressure, dP is 0, and more than that, my P has to take the pressure of the environment. Okay, and then I have T naught ds, ds is 0, so I can stop here. Okay, but this is not very useful, right? At this point, you probably don't, you are not impressed by this. Okay, so let's say this has to be 0. Availability has to be less than or equal to 0. Okay, but we can manipulate a little bit, don't worry. This is coming from here. If you remember the differential form of H, is actually PdV plus VdP. If you take the differential form of H and don't expand this to U, you will get this form, right? Because H, okay, I write one more. H is U plus PV, and therefore if you take DH, you get this line. Okay, and now dP is 0, so this term is 0, and you have du plus P dV. But P is P naught, you have this. Okay, so it turns out that this thing on the right hand side of this first line here is essentially dH. So that gives you dA is dH, and this is what we need to minimize. Okay, so again, look at this entropy, constant pressure, you minimize the enthalpy. So let's go to that table. Okay, constant entropy, constant pressure, you minimize the enthalpy. Okay, constant entropy, constant pressure, you minimize the enthalpy. Okay, I'm a bit bored now. I don't want to do all of them. I'm going to do one more, and you can just follow the same thing. Okay, you choose. Do you want Gibbs or Helmholtz? This is something you can choose. Let's don't waste time, please. Tell me what do you like to see? Are you with me? Gibbs. Okay. Okay, 3 Gibbs, 1 Helmholtz. So let's do Gibbs. Okay. Now hopefully at this point you already sense what is coming up. Okay. So I'm going to now look at. You see, I erased entropy. Before this entry was entropy. Now I want to look at constant temperature. Now constant entropy again is painful to control, right? It's a very difficult experimental parameter to control experimentally. Okay, constant temperature, constant pressure. Okay, so I erase entropy and replace by temperature. So what do I have? I have dt is 0, dp is 0, and I also want to keep the temperature to be the same as the temperature of the surrounding, and pressure to be the same as pressure of the surrounding. Okay, so let me start. And you know this is Gibbs. So I'm going to just show you this is indeed the case. So what I want to have is this. This is what I want to show. Okay, so let's write out the definition of Gibbs function. I want to write it in terms of internal energy. So H enthalpy is U plus PV, and the whole thing minus TS. Okay, very nice. You guys choose the longest one for me to do. Okay, dG will be du plus PdV plus VdP minus TdS minus SdT. Okay, let's cross out those that are 0. So dt is 0, this is gone. dp is 0, this is gone. And then I have my pressure to be maintained by the surrounding. I have the temperature to be maintained by the surrounding. So this is the definition of dA, right? dA is du plus P naught dV minus T naught ds. So I'm done. Okay, so this is dA, and we know it has to be the minimum. Okay, so this is Gibbs, and you go to check this table again. This is constant temperature, constant pressure. Constant temperature, constant pressure, you minimize this. Okay, I didn't do the Helmholtz function. You can try, you should try. It's, now you know how to do it, but still, please spend some time to do it. Okay. So finally, what do I have? I will have one more. I want to do one more. So wait a minute. This is too slow. Make it big. Okay, now I want to discuss this situation. Sorry, I didn't change this number. They are all one. I would change them before I post the note. Okay. So this is really the fifth case. I have discussed case 1, case 2, case 4. I skipped case 3, and now I want to discuss the fifth case. Okay, this is a spatial case. So this is the case where system is thermally isolated. System is not just the system plus surrounding, but system is thermally isolated. And with constant volume. What do I mean by this? I hope at this point you can already guess what we need to optimize. So I have this picture of my system plus surrounding, but I'm going to make my system thermally isolated with a constant volume. Okay, what does it mean? It means heat cannot enter the system. So in this case, I impose a very strong constraint. So heat can't enter, heat energy can't enter, and I cannot perform mechanical work. And then because of the constant volume, no mechanical work. Okay, what do I have? In this case, my internal energy cannot change, right? My internal energy cannot change. I cannot give any heat. I cannot do work. So du is 0, and dv is 0 too. Okay, so I look at it here again. I have my dA. dA is du. This is du cannot change. Okay, let me write this out because I like this so much. ds. This has to be less than or equal to 0. Okay, and now we look at the right hand side only. This is 0. This is 0. Okay, and temperature is always positive. So one thing I can conclude from here is the system entropy has to increase. This is something to maximize. But why is it not surprising? The reason this is not surprising is because I changed my universe. Originally, my universe was much bigger, and now I make my universe smaller such that my system is the same as my universe. And once I have this constraint, I have something very strong for the system. So that is the strong statement. The entropy of the system itself cannot decrease. Okay, so this is the last line here, and it concludes so this is the case. You cannot, you basically thermally isolated the system, and your entropy has to be maximized. So this is the fifth case here. Okay. All right. So why do we call this availability? We should say a few more words about this. So this is a fifth. Okay. This availability tells you what. So this availability. Why do we call why? We call this availability. Okay, that's because it gives the measure of the maximum amount of work which can be extracted from a system. So this is something like a holiday assignment for you. You need to think a little bit about this. Why do we call this availability? What I have shown is if I define availability for a system in contact with a particular surrounding, I can use this concept to relate to the kind of thermodynamic function that is useful for the particular scenario. Okay, but this is a little bit more. Why do we want to call this availability? I could have called it something else, right? I could have called it a different name, but this availability is related to work. Actually, I already show you one example, and that is the helper function. Okay, so I will write you the result, and you can think about this. Okay, the availability, this concept gives a measure of the maximum amount of work, which can be, or which may be extracted. All right, you can okay, from a system in given surrounding. Now, this kind of term is very standard in thermodynamics because you are not sure. Why are you not sure? The reason you are not sure is because you don't know about whether a particular process is reversible or not. And that's why this maybe is related to all this inequality you see. Okay, no one can tell you for certain. No, if everything is reversible, you change all inequality to equality, then this will be an exact statement. It will be a predictable amount. Okay, another point to note. Now, I give you some hint. Where can you read more? You can read page 107 of Atkins. This will have some nice discussions. And the other thing is, when we talk about system, I didn't say anything about the complexity of the system. I didn't even tell you what is the system. I just say there's something called a system. Okay, so this is so general that it doesn't place any constraint on the internal complexity of the system. So the internal complexity of the system does not affect our argument earlier. Okay, so with this, you already see this. There is the summary. And I hope you already notice the key point here. It turns out that what I kept constant, I didn't say it before, I kept it very general. You have 4 thermodynamic potentials, and it turns out that the constants that are kept, the parameters that are kept constant are the natural variables. So in this sense, it's very easy to remember. So you know, F, for example, the natural variable is T and B. Very easy to remember, like your television, your TV. Okay, and it turns out that if you want to analyze a system with a constant temperature and constant volume, you need to minimize the Helmholtz function. Okay, and the same goes with the rest. I didn't I have to emphasize that this is the end result. This is not my starting point. Okay, and some books really just jump to here and say, because this is the natural variable, you have to, if you keep them constant, you have to minimize Helmholtz function. But then the next question you ask is why? Then you have to set up this argument again. You have to set up a system, set up a surrounding, and discuss this. So the way we do it is more general, and hopefully you agree that this gives more insight. Okay, this is one piece of physics I want to present to you, and there's another big chunk that I want to begin, and that is the so-called TdS equation. So this is a set of equations. They are very useful to have. I could have, we could have treated this earlier. We could have bundled this with chapter 4, but I've decided to do it here because now if we did it in chapter 4, back then we did not have Maxwell relations. Now we have Maxwell relations, and together with Maxwell relation, we can get things very fast. And indeed, I'm going to take advantage of this knowledge now and really show you this. Okay, so this TDS equation will be something we want to discuss after the break. And let's take again a short break, 5 minutes, go to a bathroom, go and drink some water, and we come back again. Okay, now it's 1:30. Let's come back at 1:35. All right, welcome back. Okay, the final part of this chapter is this TDS equations. They are shown here, so I give you the form, but of course you can prove them. And I'm going to show you some of, I'm going to prove one or at most two, depending on the time. But why do we worry about this? Why do we care about them? Here's the reason. Sorry. Okay, I'm going to call this TDS equation 1. So it will be, I'm going to label this TS1, TS2, TS3. Okay, now, if you know that a process is reversible, these equations are actually very powerful. Okay, so this equation, if you inspect the form, the mathematical form, you can see this is the first equation. Basically, is treating S as a function of V and T. Okay, so if you know, be careful, I'm not talking about natural variable here. Here, I'm talking about this. If you know the two processes can be related by the change of V and the change of T, then the first TDS equation is the most useful. And likewise, this is a function of P and T, and this is P and V. Functional. Okay, so these are given to you. If you have a PVT system, these are the parameters you want. And once you know which ones are accessible to you, you can pick the corresponding TDS equations and calculate the TDS. Okay, why do we care about this? Okay, here is some reason. So if you have a process, if the process linking the two states A and B are reversible, so if the process is reversible, so if a process is reversible, and the two process take the process, the process takes you from A to B, and if A and B are separated by dV and dt, for example, you can calculate your TDS. And in this case, you know from second law that this is directly related to the heat involved in this reversible process. Okay, so you can calculate this part and you get TDS, and the interpretation is this is the TDS. Okay, so you get the heat transfer, reversible heat transfer. And if you want to look at the entropy change, you can take this, after you do the calculation, you divide by T, you integrate. So you integrate ds, and that gives you the entropy change, separating the 2 points A and B. So you get the entropy change like this. And the other thing, the other point, which is not yet apparent to you, maybe, but maybe for some of you, you can already see. This equation on the left-hand side is something that will give you the first 2 points. So either the heat flow in the reversible process, in a ref process, or the process, or the change of entropy. So this is the information captured by the left-hand side. These are related to the right-hand side, which are experimentally accessible information. So the left-hand side for all 3 equations are experimentally accessible. So can be related to experimentally accessible parameters. Now heat capacities are obvious. You see heat capacity here, but if you are observant, you will see these partial derivatives are also experimentally accessible. Now I don't have much time. Do you want to guess what are these partial derivatives? Just 1 minute. So these accessible parameters are Cp. You can type when I write Cv. Any guess? What are these? No? Compressibility and thermal expansion coefficient. Okay, all this can be measured, at least in principle. Okay, so let me show you. I'm going to do it in a two different ways. You can derive all this. So I'm going to derive TDS1 for you. The other thing which is more powerful, which I really hope I have time to show, is to apply this on exchange on ideal gas, and that should make you very happy because you see everything is consistent. So I'm going to derive TDS1. Okay, and I think I want to do it because I want to show you how to use partial derivatives and all these tools you have in your toolbox. Okay, so TDS1, you see I have volume and temperature as the independent variable. So I'm indeed going to write it this way. I'm going to start from here, temperature and volume. And this immediately allow me to write ds. Now this is something you have to do. You have to be able to do in your dream. At least this first line. Okay? So at least you must be able to reach this point. Okay, I want TDS, so I'm going to multiply by T here, everywhere. Okay, so this is, I don't know how to approach, how to move on now. So I have to move, I have to work a bit harder. So first, I remind myself what is the definition of CV. Okay, now with experience, you don't have to do it this way. You recognize it very quickly. Okay, and this is the definition of the heat capacity at constant volume. But this heat is heat capacity can be written as T okay, it can be written as T times the partial derivative of entropy with respect to temperature. Actually, you have seen this last time when I discussed solid. Okay, and that gives you the first term. You have your CV times dt goes in. Okay, so the first term is done. And what about second term? Second term, that is why I decide to do it now rather than before. Second term is actually easy for you because you know how to use Maxwell relation. So I'm going to use Maxwell relation to relate this to a different partial derivative. It turns out that this is a partial derivative of pressure with respect to temperature at constant volume. Okay, you see cross term is always conjugate parameters. Cross term is always conjugate parameters. And then when you have V inside, you have T outside, and you swap. Okay, this much I think it's not a problem for me. The problem is the minus sign. Okay, but I can tell you this is the correct Maxwell. So Maxwell. Okay, so this is done. The first one, first TdS equation is proved. So I will just I want to write it in the same form. So no, don't want to confuse you. So this is Cv dt plus T times this whole thing is T times this partial derivative and then dV. Okay, done. Okay, you can prove the rest. You can prove the second one. And in fact, I want to prove the third one. That is kind of cool. So the third one, TdS3. Okay, so more space. Derive TdS3. And second, TdS2, you can do it in a very similar way. Okay, because you can see the parallel here. So suppose, now the point is, I assume you do it in sequence. So TdS1, you prove. TdS2, you have, again, you prove it. So these two are correct. And TdS3 is actually, can be derived very straightforwardly if you know the two TdS, 1 and 2. Okay, so again, we write S like that. Okay, so ds will be this dp plus p dv. Okay, so because of this, I can write it like that. And I want TdS, so I give multiply by T. Okay, now here is a shortcut. The shortcut is this. I'm going to use TdS1, equation 1, TS2. So I'm going to use TS1 to think, to learn more about this term here. So if I have a constant volume process, so constant volume, what do I get from constant volume? So if I look at this, constant volume means the first term is gone. So constant volume will give me TdS is Cv dt, right? Constant volume. And what am I going to do next? This is from the first TdS. So I'm going to derive this identity. I'm going to look at this equation. I'm going to take partial derivative with respect to pressure, but keeping volume constant. Okay, constant volume. So I'm going to take partial derivative with respect to P And likewise, this dt, I'm going to take partial derivative with respect to p. I'm going to demand the process at constant volume. So I can get this result, right? So this is how I look at this. Okay, so if I use Ts2, which is a constant pressure, I will get another similar result. It's identical argument, so it's the same thing like here. But you have to change the corresponding variable, and I will get this. Okay, I'm done because this one is the first term here, and this one is the second term here. So I tidy up everything. I get my third TDS equation. So the first term is this product here times dP. So I have C constant CV partial T partial P constant volume and then dP plus the second term. This one is the second term. I have CP okay. All right. Now this is done, and I hope you will spend time to look at these equations yourself. Maybe you can also try to derive it differently. There are many ways to do things. Okay, now I want to come back to this point, these experimental accessible parameters. You already see two. You have already seen CV and CP. So I'm going to really write it in the way that we understand. Okay, so first, I want to write a little bit more. So a reminder is the following. So this is a reminder. We define beta to be 1 over V, partial derivative of volume with respect to temperature at constant pressure. Okay, so this is the coefficient of volume expansion, thermal expansion, right? You change the temperature, volume change, and it's defined like this. So you don't have a unit of volume. So this has the unit of per Kelvin. Okay, this is something we have seen in chapter 1. And then kappa is 1 over V, partial V. So this is the response of your system with respect to pressure. Okay, and we like to define it with a minus sign here to make kappa positive. So this is isothermal compressibility. This is compressibility. This is the volume expansion coefficient. Okay, this is the reminder up to this point. Huh? I want to write something more. Okay, so if you look at this, you understand the statement I made earlier. What is the first line here? The first line is temperature. Actually, if you can show, I hope you know how to show. So this is this partial derivative turns out to be beta divided by kappa. Okay, how do you show this? Just type the word for me. Don't need to show. Just you have seen this before. So just help me complete this. How do you? Thank you. Okay, I already get 2 answers. This is reciprocity. Okay, the product of 3 partial derivatives gives you -1. That's why you can kind of guess already this minus sign disappear in the end. Okay, you use the reciprocity theorem, you can show this, and therefore this is beta divided by kappa dv plus cv dt. So this is very good news. Everything here is really experimentally accessible. Everything here. You can do experiment to measure all this. Okay, and the second TDS equation will give you TV times beta. Is it correct? So this V times beta will be this. Okay, that's correct. And with a minus sign here, dp plus cp dt. And the third TDS equation is CV kappa divided by beta dp plus okay. So the highlight here is highlight for here. Right hand side are experimentally accessible. Okay, next. The next part I want to do is to test these equations. And that would be nice. Once you test and you find consistency, you will have a much more enjoyable Lunar New Year. I already kind of show you this must be correct. But the more important thing is to get something you are really familiar. Okay, so I'm going to try on ideal gas. So for ideal gas, you know how to write beta. You put in the equation of state, PB is NKT. You get 1 over T, and kappa is 1 over P. Okay, so we are going to really try this. And in fact, it's not very good management of my whiteboard here. Okay, I'm sorry, I might have to flip back and forth between, okay, let me see what I can do. I want this equation, really. Okay, so I'm going to use it as a test. So I'm going to look at the example, ideal gas. I'm going to test this to show you get the familiar result. Okay, TDS1. TS1. What do you get? So from TS1, let's just play with this equation. I will have TDS. On the left-hand side, I cannot do much. That's the point, because this is something I don't really know how to control. But the right-hand side, I can control everything. So I just plug in all this. So I have temperature. I have beta divided by kappa. That will be P over T, right? So this will be P divided by T. And then dV, I cannot do much. Let's just keep it. CVDT. You should remember, I actually said twice already in the past. For an ideal gas, this can be very easily calculated. This turns out to be du. Okay? All right, so what do we get? We cancel this t and we have pdv plus du. Okay, what is the familiar result I want to present to you? This is the familiar result. I rearrange, I get du is TdS minus PdV. So I take my TdS equation, plug in the ideal gas result, I get the first law. So I'm happy. Okay? So let's try the second one. So the second TdS2, hey, what did I do? TdS2. I take the second TdS equation and do the same thing and play with that. Left hand side, I cannot do much. Right hand side, I have minus t, I have v, I have beta. Why is beta is 1 over t dp plus cp dt. And by now you should know how to, okay, the first, okay, let me cancel the t first. I have vdp. And what do I have here? This is cp times dt has the parallel of dh, right? This is, if you analyze the change of enthalpy following the same argument, you get this result. So cp dt is dh. Okay, what is the familiar result I get? I get the definition, the differential form of dh. I have TdS plus VdP, and this again, you know, must be correct. If you don't trust me, just go back to a few slides earlier. You will be able to see. So this is again consistent. Okay, I don't. This is again messed up. Okay, doesn't matter. I will arrange this later. Okay, next I will continue and try this, but if I do it once more, you'll be very bored. So I'm going to try something else to show you, to find the consistency you will recognize. Okay, so TdS3, I'm going to do something else. I'm going to use it to look at, this shows you the power, how powerful these equations are. So I'm going to look at adiabatic case, adiabatic process. Okay, an adiabatic change from state A to state B, and A and B are separated by dP and dV. Okay, so on the left hand side is adiabatic, so I have 0. On the right hand side, I have this CV, kappa divided by beta, which is kappa divided by beta is T over P, right? T over P. And then I have dP. Then I have 1 over beta divided by V. 1 over beta will be T, so I have T divided by V. Okay, so I'm playing with TdS3 now to look at an adiabatic process. Okay, temperature I can cancel, so I will cancel them. And I'm going to write it like this. So the next line I want to write is I'm going to put this P inside the differential. So I have my CV log P, log P plus CP log V has to be 0. And I want to then divide by CV. So I have CP divided by CV log, sorry, D. So this is D log B. So there's a D here. And this has to be 0. And now you know what I'm going to do. I'm going to define the adiabatic index, adiabatic process, adiabatic index. This is the ratio of heat capacities. All right, so this is D log P. I move it to the other side. I will have minus gamma D log V. Okay, and now I integrate. I integrate from process 1 to process 2. So I can integrate like this. I can integrate from 1 to 2. So they will take P1, P2. This will be V1, V2. Okay, so I will have log of P2 divided by P1 is the same, is equal to minus gamma log of, okay, minus is here, so I will still have V2 over V1. Okay, I put this minus sign in to change, to flip the ratio. So I will have B1 divided by B2 gamma. Okay, sorry, bad management of the board. So here I have P2, P1 is the same as V1 gamma, V2 gamma. So I group all the ones together, I get, or in all the twos together, I get PV to the gamma is a constant. Okay, and I hope you agree with me. This is something you recognize and something that will really show that everything is nice and under control. Okay, this is example 1. Very long example, but I really like it very much. And I chose 3 to show this because I think everyone remember this, PV to the gamma. And it's not that easy for the expression of T and V. So, but this is a nice one to remember. This is completely nonsense, this board. Okay, now this is done. And one more example, and I'm happy to stop. Sorry. I don't want this. Phase transition has to wait. Add. Okay, example 2. Example 2 is kind of cute. When we talk about these heat capacities a long time ago, I ask you to show. I ask you to show Cp minus Cv is V times T times beta squared divided by kappa. Okay, this is in one of the assignments. You probably did it in a very long way. That is fine. That is good. I'm happy to know that. But now, after you learn Maxwell relation, you can do it very quickly. So this is what I'm going to show you. Okay, so I'm going to now my aim is to find heat capacities. So this is always the trick. We want to find a way to write heat capacity down very quickly. So I will start from S as a function of T and V. Okay, so I can write ds. So I want to introduce one first. Okay, you will see what I mean. Let me do it quickly. So T V dt plus. Okay, you know this much. Everybody knows this much. Now, the good news is you can already sense, you can already detect heat capacity, right? I will be able to manipulate the first term and get me heat capacity. And this heat capacity is a constant volume. Okay, but I want constant volume and constant pressure. So let's see how we can do that. I'm going to assume I'm going to divide by temperature at constant pressure. That is to say, I'm going to introduce the partial derivative. Right? I'm going to look at the change against temperature, but this process will be evaluated at constant pressure. Okay, and this is sometimes in books, in mathematics in particular, they say like this in words. They will say I divide by dt at constant pressure. So you have to do it like that. Okay, it's still this process depends on what parameter you keep unchanged. There's the pressure. Okay, so I'm going to do this partial derivative. We cannot change anymore, and you divide by dt, so it's gone. And partial derivative, we don't change anymore. Actually, I say something like this at the very beginning of this course. How do you evaluate this? So I'm going to look at the change with respect to temperature at constant pressure. Okay, so now I'm going to multiply by T everywhere. And this immediately give me Cp. Sorry. So this is heat capacity at constant pressure, and this T times this whole thing is heat capacity at constant volume. I'm nearly there. Plus this T. Now, what else can we do? Here, you can at least recognize a few things here. This is the change of volume with respect to temperature. Okay, so this second term here must be related to beta, right? This is a kind of thermal expansion, the change of volume in response to temperature. So this is thermal expansion, but it's not the way we define beta. We define it with a factor of 1 over V. So this whole thing is V times beta. Okay, and what about this? What is this? This, that is the key. Without the machinery of this chapter, you will have to really work this out. But now with all the tools you have, you can use Maxwell. Again, this is Maxwell, one of the Maxwell relation, this partial derivative. And you have this. Okay, Maxwell relation, you see this at the top is entropy, at the bottom is temperature. And this is volume, and this is pressure at the top. So this is one of the Maxwell relations. Okay, now if you have ideal gas, sorry, I have to say for ideal gas. No. Sorry. This is more general, sorry. Now, so from here, this is the partial derivative I gave earlier. Using the reciprocity theorem, you get. Okay, so this is beta divided by kappa. Now you plug in everything, you get a volume, a factor of volume, factor of volume. One beta from here, one beta from here, so you have beta square, and then you have kappa in the denominator. So this is done. Only a few lines. Okay, and in the past, maybe you do it. Now, without this line, you might have to go through a much longer argument. Okay, so good. This is a good progress. So before I let you go, I want to invite you to read the end of chapter 16 of Blundell and Blundell. So this is near the end. Why do I invite you to do that? Because there, this book gives you a few pages of tips on how to solve thermodynamic problems. It will ask you how to, you need to, for example, identify the heat capacity, and there's one way to do it. And as soon as you can, you have to identify the Maxwell relation. So this is something very useful for you. So reading assignment, read this. Okay, so with this, I'm done, and I wish you a very happy vacation. Thank you very much.